obviously, where we're bringing in bands and lecturers and belly dancers and all sorts of stuff. So thank you for coming out to try out this new thing and whatnot. Up first, we have the esteemed Mr. Bill Hurley of the Columbus Astronomical Society, an amateur astronomer, poet, and entertainer who's going to be talking about the size of the universe. He is more than happy to field questions on the fly, so if you have a thought or a question and need an explanation, don't be shy about raising your hand or shouting obscenities at the stage or whichever. So without further ado, Mr. Bill Hurley.
Glad to be here. My name is Bill Hurley, as the slide says. I'm with the Columbus Astronomical Society out of Perkins Observatory in Delaware. Wanted to tell you that we're going to do a really quick trip through the universe in about 20 minutes and in about 11 steps. And wanted to start out by just saying that astronomy is the oldest science in the world, and there's a bazillion topics that you could talk about, but we're only going to talk about one, is how big is the universe. Now, Occam's razor would indicate that the simplest explanation is usually the right one. So the honest answer is we're not sure, but we know this much. It's big. It's very big. It's really, really big. That part we can get across. And I will also tell you that it is, as we speak, expanding. So by the time I end this lecture, it will actually be bigger than when I started. So it's going to be a little bit difficult to put an actual size on it. So our goal is really to appreciate how big the universe is. And we're going to do it in two ways. One is by showing the scope by its structure and relative size. And the others, we'll talk a little bit about time travel and distances. The actual 11 steps come from Terence Dickerson's book, Night Watch, Chapter 2, The Universe in 11 Steps. And I want to first start out by describing what is a step. The step that we're going to talk about can be described very simply. If you look at this picture that I took up at the Park of Roses, the important part isn't the fact that it's a particular rose. What's actually the dimension here is that this picture is 12 inches wide. So that's our first step, and what I'm going to do is step backwards and take another picture that is 100 times as wide as the previous picture. So when I do that, I now have a 100-foot wide picture, which I had to get on top of the gazebo to take. So that's the first step, from step 1 to step 2, 100 times further back. Now the problem is, of course, if I go 100 times more, then I end up, you're not really going to even see the Park of Roses anymore on land. So what I'd rather do is employ Google Earth and go up 15,000 feet, and now I'm looking at approximately 2 miles of real estate, of which, if you know your part of North Columbus, you can see the Park of Roses there. So now we're step 3, we're actually 10,000 times wider a picture than we started with when we had a 1-foot square. If I go 100 times on the next step, I'm now covering the entire state of Ohio, and another 100 times I have stepped back, I've got the entire planet. So in 5 steps, I've gone from a 1-foot wide picture of a rose to the entire planet Earth 100 times. And that's basically how we're going to step through the universe. We're going to make it from the planet Earth to the edge of the universe in 11 steps. And we'll see what we discover along the way. So step 1 is we are going to start with the Earth. It's 8,000 miles wide. And I want to get across a particular idea here that I think most of you are pretty familiar with, that light travels at 186,000 miles a second. The reality is that when we are talking about distances in outer space, we can't use miles because the numbers are just way, way too big. So instead of talking about linear mileage, we talk about the time it takes light to travel. And that's how we distinguish our distances. To put it in terrestrial terms, if we had a space shuttle that could orbit the Earth, which we do, we've had many, it takes them about 90 minutes to make one orbit. If we were traveling at the speed of light, that space shuttle would travel 7.5 times in 1 second. So that's the speed of light, 7.5 times around the planet in exactly 1 second. And so that's the speed we're going to be going at as we begin to describe these particular distances. So what we're going to start with is a 100, we're going to start with this one cube. And in this cube, it's going to be like a nesting set of boxes, and we're at the innermost box. This box is containing the planet Earth. That's our first step. Now, if we multiply that box by 100 times wider, 100 times taller, 100 times deeper, make it that much bigger, it will contain not only the Earth, but the orbit of the moon around it. The moon, in terms of light distance, is actually 237,000 miles on a given day, but it takes light 1.27 seconds. So when we're talking astronomical distances, we say the moon is 1.2 seconds away. And that's how far light would need to travel in that period of time. Just as a side note, it takes the lunar orbit 27.3 days to complete its orbit. So now our step 2 box contains the Earth and the orbit of the moon. Let's multiply it by 100 times, and now we have another box, again visioning nested boxes. This particular one does not have the entire solar system, but it does, if we put Earth in the center, contain the orbits of Mars, Venus, and Mercury. Mars, incidentally, is 3 minutes away, using the light speed ratio. Venus is 2 light minutes away, Mercury is 4.3, and the Sun is 8.3 minutes away. What that means is if you're out having a suntan, and somehow the sun gets turned off, turn over, because you got 8.3 minutes left before everything gets very dark and very cold. So that's basically how far the sun is away. We refer to it as 8.3 minutes. Now let's take this cube, multiply it 100 times, and now we have a cube large enough to contain the entire solar system. And as you can see by the ratios down at the bottom here, we're 1,000,000 times the size of the original cube that contained the planet Earth. It's now containing the whole solar system, and we are now here. What's the name of it? Beyond Pluto. Beyond Pluto. That's right. This particular cube is now containing that space just beyond Pluto. Actually, it would take 17 light hours to get to that outer orbit. That happens to be 11.3 billion miles, and that's the last time I'm probably going to mention miles, because as you can see very quickly, it's going to get off the chart. So we're going to multiply now this cube that contains the entire solar system, something that takes 17 light hours to get across, and we're going to multiply it by 100 times. And this is the most exciting step of all. This is where the real surprise comes. When we multiply that cube 100 times, we get nothing. There's nothing there. It's still just the solar system. This tiny little speck now in the center of this very, very large cube. Now, this cube would take 70 days to get across if we were traveling at the speed of light. And the sun is the only star in that very vast chunk of space. Go another 100 times, and you can see by those numbers at the bottom of the screen we're many, many, many times greater than that original cube that covered the Earth. Now we're starting to pick up a few stars, among them Alpha Centauri. Alpha Centauri is the closest star to Earth. It is 4.2 light years away. Simply means if the sun is 8.3 minutes away, the nearest star is 4.2 years away. That's how they compare. Sirius, the brightest star in the sky, is in fact in this particular distance, as is Epsilon Eridani. Epsilon Eridani, you probably haven't heard of. It is of interest of more modern days because it is one of the first systems that have been discovered as exoplanets, meaning we're finding planets around that star that have potential for being life-supporting. So there's a great interest in that right now, and that was one of the first ones that was discovered. So there's another star out there. I don't happen to have it in this particular field. It's called Vega, and Vega is 25 light years away. And I want you to imagine for a moment that you have a pen pal or a text message pal or a Facebook friend on Vega. And so you get out your text message and you send this text message to your friend who is existing in the Vega system. Let's say this year you type, "How are you?" In the year 2038, they receive the message and they say, "Bored, LOL." And it comes back to you in the year 2063, "Me too." That's how long it would take a text message to go back and forth, only 25 light years out, because that's exactly how long each pass would take, 25 years. That, incidentally, for those of you who are Carl Sagan fans who saw the movie Contact, the Vegan system was the one that they were looking at. It was also, we sent a film out there in our early television days of the Berlin Olympic Games. 50 years later, we're getting the Berlin Olympic Games back from the Vegan system with some embedded code in it. That was Sagan's way of saying this is a 50-year round trip to the Vega system. And that setting of that film was 1986 from the 36 Berlin Games. Just a little side note there. So we're going to go to step 7 now, and now we're picking up a lot more stars. Step 7, we're still in our own galaxy. We're many, many millions of times bigger than our original cube. We're picking up some of Orion's stars, the Orion Nebula, Deneb, and Aldebaran, pretty well-known stars that a lot of people look at today. M6 and M7 are clusters. Beehive cluster is in this particular group. Basically, we're picking up some more bulk. Beehive cluster on the left, Orion Nebula on the right. That would be items that are in this particular real estate that we are looking at this step. Those of you who are familiar with the Orion constellation, I point this out because if you happen to, even with just a simple pair of backyard binoculars, go out and look at this position in Orion's belt, you will see that image even with a simple pair of binoculars. That may be, if you don't own a telescope, the easiest thing to see without a backyard telescope. So something to consider if you'd like to see it. Very, very easy to see, and mostly fall, winter, and early spring sky. We're going out now 100 times bigger, and at last we now encompass the entire Milky Way galaxy. Reality is that the Milky Way galaxy of which we exist, and we happen to be right about here in one of these arms, about a third or fourth of the way in. This entire galaxy is around 100,000 light years across. To put it in simple terms, you could travel at the speed of light, it would still take you 100,000 years to cross the Milky Way from one side to the other. There are approximately 200 billion stars within, and guess what? They're all about as far apart as we are to Alpha Centauri, which is about 4 light years between. So it gives you an idea how much space we're talking about. Up until the 20th century, astronomers thought that the Milky Way galaxy was the universe. They didn't realize that it was one of several billion. As I said, we're about a quarter of the way in. One thing I want to point out, just to give you an idea, people go out to me and say, "Hey, I looked in the sky last night, did you see the Milky Way?" Yes, I see the Milky Way every time I look any direction. I'm in the middle of it. We're all surrounded. What you see, what people refer to, is that center core dust lane that is appearing across the elliptic of the sky. Very, very pretty. I was actually in Arizona last November, and the Milky Way threw a shadow. It was a moonless night. There was a shadow on the ground coming from the Milky Way. That was really cool. Jupiter was also throwing a shadow that particular night. one thing I want to mention about, just to put everything into a size perspective, if we reduced the universe to a size that allowed the Milky Way galaxy to touch both the Pacific and Atlantic Ocean, in other words, if the Milky Way were reduced to the size of the continental United States, the solar system would be the size of a quarter. So that's the difference between the solar system and the Milky Way galaxy, is the difference between a quarter and the continental United States. So now you get some sense of how much size we're talking about. Okay, we're only at step 8 in the universe. We're going to take this cube that can contain the entire Milky Way galaxy. We're going to multiply it 100 times again. And now what we do is we start to pick up some other galaxies. The closest one is Andromeda, M31, and it is 2.5 million light years away. The closest galaxy is 2.5 million light years away. So when you're looking at a telescope and see the Milky Way galaxy, or even if you're looking at a photograph of it, the light that struck either the camera or the observer's eye is over 2.5 million years old. Which means, and I always get asked this question of Perkins, does that mean that if that light went out 1 million years ago, you would still see it for 1.5 million years? The answer is yes. That's exactly right. So we don't know when we're looking at Andromeda right now if it still exists or not.